All right, let's dive right into this explainer where we're going to completely demystify the equations of motion. We're going to treat these equations like a mathematical summit that we can conquer using three completely different paths. If you've ever looked at a physics problem and wondered how on earth motion is actually quantified, well, you are in the exact right place. Today, we're taking one core set of ideas and seeing how algebra, calculus, and geometry all lead us to the exact same beautiful destination.
Here is the roadmap for our climb today. We'll start with the rules and the symbols, lay out the three final equations, and then hike our three paths: the simple method, the calculus method, and the graphical method. Finally, we'll wrap up with some crucial points you absolutely need to remember.
Okay, first up, the rules and the symbols.
Before we even take a single step, we have to pack our gear. And by that I mean memorizing our basic toolbox of symbols. We've got U for initial velocity. That's where you start. We have V for final velocity, where you end up. Then there's A for constant acceleration, meaning your speed is changing at a perfectly steady rate. We'll use T for the time taken, and finally S for displacement, which is the actual straight line distance you've covered. If you lock down these 5 letters, you literally hold the keys to the entire universe of basic kinematics.
Moving right along to section 2, the 3 final equations.
So here is our summit. These 3 equations are the ultimate universal truths of uniform acceleration. Number 1, V equals U plus AT. Number 2, S equals UT plus 1/2 AT squared. And number 3, V squared equals U squared plus 2AS. I want you to burn these into your mind right now because we are about to prove them 3 completely different ways. They might look like just a random jumble of letters right now, but trust me, by the end of this, you'll see exactly how they are built from the ground up.
Let's start climbing. Section 3, Path 1, the simple method.
For this first path, we're just going to use standard, straightforward algebra. Think about the most basic definition of acceleration. It's literally just the change in velocity over time. So A equals final velocity minus initial velocity, all divided by time. If we just multiply both sides by time, t, we get V minus U equals AT. Add that U over to the other side, and boom, we have our very first equation. V equals U plus AT. See? It's perfectly logical.
Now, how do we find displacement for our second equation? Well, we just take the average velocity and multiply it by time. Since our acceleration is constant, average velocity is simply the starting velocity plus the final velocity cut right down the middle, divided by 2. So we plug that into our displacement formula. And remember that first equation we just solved for final velocity? If we swap out that V with U plus AT and just do a little algebraic cleanup by distributing the terms, it beautifully unlocks the second final equation. Displacement equals UT plus 1/2 AT squared.
Let's do one more algebraic substitution for the grand finale of this path. This time we take that first equation and rearrange it to isolate the t variable, which gives us time equals V minus U over A. Swap that back into our basic displacement formula. When we multiply everything out, we get this incredibly elegant difference of squares on the right side, V squared minus U squared. A quick shuffle of the terms, and just like that, we've successfully scaled the third peak. V squared equals U squared plus 2AS. And that is the algebra path entirely completed.
All right, let's wipe the slate clean for section 4, Path 2, the calculus method.
Calculus is the language of continuous, instantaneous change. So here, acceleration is the derivative of velocity with respect to time, A equals dv over dt. If we just rearrange that to dv equals a dt, we can integrate both sides. We integrate velocity from our initial u to our final v, and we integrate time from 0 to t. Now, because acceleration a is a constant, it pops right out of the integral. The math settles, and like magic, we land right back at our first equation, v equals u plus at.
So what about displacement? Well, velocity is the instantaneous rate of change of displacement, right? ds over dt. We can take that v and replace it with the u plus at that we just proved. This gives us ds equals u plus at all multiplied by dt. If we integrate that entire function over time, from 0 to t, the calculus flawlessly constructs our second equation. The integral of u becomes ut, and the integral of at becomes 1/2 at squared. Absolutely brilliant.
For the third calculus derivation, we get to use a really clever chain rule trick. Instead of expressing acceleration with respect to time, we can relate it directly to displacement by writing a as velocity times the derivative of velocity with respect to displacement. So a equals v times dv over ds. Rearrange that to v dv equals a ds and integrate both sides. Evaluating that integral gives us v squared minus u squared all over 2 equals as. Multiply both sides by 2, and our integrals bring us straight back to the third equation. Calculus path complete.
Now, for my personal favorite, Section 5, Path 3, the graphical method.
We are putting away the standard algebra and the complex calculus to use pure visual geometry. What's absolutely fascinating here is that a simple velocity time graph contains every single answer we need, literally hidden right there in its shapes. On the vertical axis, you've got velocity, starting at u and rising up to v. On the horizontal axis, you've got time, t, and a straight diagonal line connects our start and end points.
Think about the slope of that line. The slope of a velocity time graph literally represents acceleration. Slope is just rise over run. The rise is your change in velocity, v minus u. The run is your time, t. So a equals v minus u over t. By just calculating the physical slope of that line visually and rearranging it, we get our first equation of motion, v equals u plus at. No heavy math required, just reading a graph.
And it gets better because this brilliantly illustrates how calculating the physical area under the graph geometrically builds our second equation. The total area under a velocity time graph equals your displacement. If you look at the shape under our line, it's a trapezium. The area of a trapezium is 1/2 the sum of the parallel sides, which are u and v, multiplied by the base, which is t. Substitute our slope equation in for v. Simplify the geometry a bit, and there is equation 2. Displacement equals ut plus 1/2 at squared.
For our final equation, we start right back at that same trapezium area formula. Displacement equals 1/2 of u plus v times t. But this time around, instead of substituting v, we swap out t using our slope relationship where t equals v minus u over a. Replacing the time variable in our visual area calculation gives us a super familiar algebraic setup. We multiply it out, get our difference of squares, and it brings us right to the final equation. V squared equals u squared plus 2as. Proving beyond a doubt that geometry works exactly as well as calculus and algebra.
Almost at the finish line. Section 6, crucial points to remember.
We've reached the summit 3 different ways, but before we wrap up, we need to solidify the vital rules for when these equations actually work. The absolute most crucial point to take away today is that these paths completely break down unless your acceleration is perfectly constant. If the rate of acceleration is changing even a little bit, these equations are off the table. Furthermore, all quantities must be along the same straight line. We are strictly dealing with one-dimensional kinematics here. The minute motion starts curving, you're going to need a different map.
Also, I want you to remember this critical translation secret for solving actual practical problems. If an example tells you a body is accelerated uniformly from rest, that is basically a cheat code. From rest is the universe's way of telling you that your initial velocity, u, equals exactly 0. That makes the math infinitely easier, because half your terms will just vanish into thin air. And there you have it. We have scaled the mountain. Whether you use the straightforward step-by-step logic of simple algebra, the elegant continuous flow of calculus, or the visually intuitive shapes of geometric graphs, the universal laws of uniform acceleration remain absolutely identical. The underlying truth doesn't change. Only the lens we use to look at it does. So I'll leave you with this to ponder. Algebra, calculus, or geometry? Which of those 3 mathematical paths made the most intuitive sense to your brain?